A complex power series is a series of the form where we sum from k equals 0 to infinity a sub k z minus z naught to the kth power, which I can expand this way. And z naught is some fixed complex number. Typically, we say that the series is centered at z naught. So this is very similar to a real valued power series, except we use z to denote complex numbers, and the a's can also be complex numbers as well. Now we've seen already, we know from calculus, that a real power series has an interval of convergence. Every complex power series doesn't have an interval of convergence, but it has what's known as a disk of convergence. And in calculus, we found the interval of convergence using the ratio test. We do exactly the same thing for the complex power series, but instead of using the absolute value, we replace it with the modulus, which is a generalization of the absolute value. So let's take a look at the power series where we sum from k equals 1 to infinity, z to the k over k squared. If k is 1, we would have z. If k is 2, we would have z squared over 4. If k is 3, we would have z, darn it, to the third over 9, and so on and so forth. Okay, so the kth term, again, we put modulus around everything. K is positive, so I don't need to put a modulus around that. The kth term is the modulus of z to the k over k squared. The k plus first term is what I would obtain if I replaced every k here with k plus 1. So I would have the modulus of z to the k plus 1 over k plus 1 squared. Now we're going to take this term right here, and we're going to divide it by that term, and then we're going to take the limit, just like we did for the ratio test in calculus. So here's the k plus first term coming from there. Here's the kth term coming from there. So I take this fraction, divide by inverting and multiplying, and I get something like this. And you'll notice that the modulus of z, a good chunk of that, cancels, so we're left with the following. Now, if we were to expand the bottom, we'd have k squared plus 2k plus 1. And basically, as k gets really, really large, k squared over k plus 1 squared is basically going to be 1 in the limit. So this entire limit is just the modulus of z, because that's constant with respect to k. Now, the ratio test tells us that the limit we get at the end, if that limit is less than 1, we know that the series converges. If the limit is greater than 1, we know the series diverges. If the limit equals 1, we don't really know. So this will be less than 1 if the modulus of z is less than 1, which tells us that the series we have above not sure where this is coming from. Okay, this tells us that our series up here, 2, converges if the modulus of z is less than 1, and it diverges if the modulus of z is greater than 1. So the series converges for all complex numbers in the open unit disk. Now here's the sticky part. That is when the modulus of z is 1. When we do the real power series, we only have to check 2 endpoints. But in the complex setting, we need to somehow account for all z on the unit circle. There's not just 2 endpoints, there's infinitely many points on the boundary of that circle, and that's where things get pretty tricky. But in some cases, this is easy, and so the following result is going to prove quite useful. Let's say we have a power series and we put the modulus around the terms that we're adding. If that series converges, then so does this series. The terminology we're using is that this series converges absolutely, which may be a term you recall from calculus. So let's apply that here. In our example, we know that if the modulus of z is 1, then we get this 1 over k squared. That's a convergent p-series. So that tells me if I look at any point on the unit circle, because the modulus of z is 1 on the unit circle, and this series converges, we know that this series will converge for any z on the unit circle. So, in other words, the disk of convergence in this case is the closed unit disk. It's everything in the unit disk plus the unit circle as well. And we're making important use of the fact that if the modulus of z is 1, this becomes 1, so we have a convergent p-series. Let's take a look at another example. This one's going to be a little bit stickier. The sum from k equals 1 to infinity of z to the k over k. If k is 1, we'd have z. If k is 2, we'd have z squared over 2. If k is 3, we'll have z to the third. Darn it, I did it again. Oops, I did it again. Z to the third over 3. Okay. Now we could use the ratio test just like we did on the previous page to show that this series converges when the modulus of z is less than 1. Now what about if the modulus of z equals 1? We know that if z is 1 itself, we would have the series 1 over k from k equals 1 to infinity, and that's a divergent p-series. On the other hand, when z is negative 1, we would get this series, minus 1 to the k, and this is an alternating series. So we know that the series converges if z is negative 1. We know the series diverges if z is 1, but there are lots of other points on the unit circle. Let's suppose z is I. If we substitute I in to this series, if k is 1, we get I. If k is 2, we get I squared, which is negative 1. And we'd have a 2 there. If I is 3, I to the third is minus I over 3. If k is 4, we'd have I to the fourth, which is 1 over 4. If k is 5, we'd have I to the fifth, which is I over 5, and so on. So you can see how the terms alternate between pluses and minuses and between i's and no i's. We could rearrange this series to look like the following. We could collect all the terms without I, put them in here. We could collect all the terms with I and put them in here. So let's just verify this. If k is 1, we'd have minus 1 over 2. If k is 2, we'd have minus 1 squared over 4. That's 1/4. If k is 3, we'd have minus 1 to the third, which is minus 1 over 6. So this series accounts for that term, that term, that term, and so on. Now let's take a look at this over here. If k is 0, we'd have minus 1 to the 0, which is 1, over 2k plus 1, so this whole thing would be just, if k is 0, we'd have 1 over 1 times I, which is what we have there. If k is 2, we'd have minus, if k is 1, we would have minus 1 to the first, which is minus 1, over 3. That would be, so minus 1/3, and that would be multiplied by I. So what we've done is we've rearranged the series. Now this is an alternating series, and this is an alternating series. And I'm going to leave out the details, but these two series, this one and this one, using tools from calculus, those two converge separately by the alternating series test. So that means the series as a whole converges if z is I. So we know that this series converges if z is I. We know that the series converges if z is negative 1. We know that the series diverges if z is 1. We've only tested 3 points on the unit circle, of which there are infinitely many. So you can see how things get quite complicated, and there's no easy answer in general. Okay, let us now talk a little bit about what are known as geometric series. So a complex geometric series takes the form a plus ar plus a squared plus ar to the third, so on and so forth. It is exactly the same formula that we see in the real setting, except now we allow a and r to be complex numbers. We call r the common ratio, and just like in the real setting, the series converges provided the absolute value of r is less than 1. But now, instead of using the absolute value of r, we need to think of the modulus of r as being less than 1. And when this is the case, we get the geometric formula, the same formula that we had in calculus and pre-calculus. So let's take if r is greater than or equal to 1, the series diverges. If r is less than 1 in absolute value, it converges. So let's take a look at an example. The infinite geometric series 2 plus I over 3 plus 3i to the k, 3 plus 3i to the k power. So when k is 0, I would have that. If k is 1, I would have this. If k is 2, I would have this. So we can see that a is 2 plus I. Now, r is 1 over 3 plus I, because this is the same as 2 plus I times 1 over 3 plus 3I. This is the quantity 2 plus I times 1 over 3 plus 3I squared, so on and so forth. Now, in polar form, 3 plus 3I is 3 root 2 e to the I pi over 4. That means that when I take the reciprocal, I invert this. So my r, which is 1 over 3 plus 3I, is going to be 1 over 3 root 2 times e to the minus I pi over 4. And the modulus of that is 1 over 3 root 2, which is less than 1. So that tells me that my series converges. It converges to a over 1 minus r. Now this looks a little bit messy. I'm going to leave out some details, but you can simplify this and actually show that this simplifies to be 33/13 plus I times 9 over 13. Now our ultimate goal is to take a function and expand it into the form of a power series, a special type of power series known as a Taylor series. But the geometric series is really going to help us a lot. We're going to basically apply it in reverse. So here's an example. Express the function 1 over 1 minus 2z as a power series centered at the origin and determine the disk of convergence. So we have a convenient geometric series formula. A over 1 minus r is this, provided r is less than 1 in modulus. So what we're going to do is we're going to take this function, we're going to identify a with 1, and we're going to identify the r with 2z. So if we take this and we substitute 2z in, we get 1 over 1 minus 2z equals the sum from k equals 0 to infinity 2z raised to the kth power. And I can simplify that just a little bit to be the infinite series of 2 to the k times z to the k. Now, when we made the substitution going from here to here, we were assuming that the modulus of r is less than 1. In other words, the modulus of 2z is less than 1. But that's the same thing as saying the modulus of z is less than 1 half. So that means that this formula, this power series formula, is valid if the modulus of z is less than a half. Otherwise, this power series diverges. We're using the geometric series there. Let's take a look at another one. Express the function 1 over 1 plus z squared as a power series centered at the origin and determine the disk of convergence. I didn't use the word disk of convergence before, but in this case, the disk of convergence is the disk of radius 1/2 centered at the origin. Now we're going to use the geometric series formula again, but a is going to be minus 1, and r is going to be minus z squared, because minus z squared, if we substituted that in, we'd have 1 minus a minus z squared, which is plus z squared. So if we use our geometric series formula and substitute it in, we get something like that. We could rearrange this. It's minus 1 to the k times z to the 2k. And we know that this converges. This substitution is valid if the modulus of minus z squared is less than 1. So the series converges if that is true. The series diverges otherwise. And the modulus of negative z squared is the modulus of z squared, which is the modulus of z quantity squared. So that means that the open unit disk is the disk of convergence. Final example. Express the function z over 2 plus z as a power series centered at the origin and determine the disk of convergence. Now this has kind of a geometric flavor to it, except we don't have 1 minus something in the bottom. We've got that z above, but we're going to do a little bit of algebra. First, we're going to take z over 2 plus z, and we're going to write it as z over 2 times the quantity 1 over 1 plus z over 2. Now, if I was to multiply this, I could check, because I'd have z in the numerator. 2 times 1 would give me 2. 2 times z over 2 would give me z. So these two are equal. Now I can expand this as a geometric series. When I do so, I get the following. I've got my z over 2 out in front still. I have minus z over 2 to the kth power. I could clean this up a little bit. This is minus 1 to the k times z to the k over 2 to the k. And then I can multiply inside to get minus 1 to the k over 2 to the k plus 1. And I'll have z to the k plus 1. So that's a power series expansion. And that is valid. We made the substitution going from here to here. That's valid if the modulus of minus c over 2 is less than 1. The series diverges otherwise. So that means that the disk of radius less than 2, centered at the origin, is the disk of convergence. And we will discuss more examples like this in class.